Searching is one of those tasks that is tedious and slow for a human, but can be automated by a computer. When we're storing so much data in a database or other format, we need a way to access that data by some criteria. There are different algorithms for searching. There may be different ways to approach searching based on the type of data structure that you are searching in, and whether the data in that structure is sorted or not. The easiest to implement is a search from the beginning to the end of a list, checking each item in order. But this search is pretty dumb, so how could it be improved? If the list is in alphabetical order, it might come to mind that we could check the first letter and decide whether to search from first to last or last to first. Or maybe we could look at the middle element of the list and take away half of the list before we even start doing a lot of searching. Or we could store the list of names in a different data structure to make it easier to search for items without covering the entire list every time. What if you want to store your data like this? Notice that everything is sorted so that on the left would be less than the node, and to the right would be greater than the node. This would be a binary tree. For the binary tree structure, there is a collection of nodes. Each node in a binary tree can have 0, 1, or 2 children, but no more than that. We could implement a data structure like this utilizing pointers. Each node would point to its left node and right node. When inserting a new element, we can keep the tree sorted by looking for where it belongs in the tree, instead of just arbitrarily placing it at the end of a list. So, when we want to insert a new element, we need to traverse the tree to find an appropriate position. So for inserting the value of 8, we'd start at the root node, and in this case it's a 5. 8 is greater than 5, so we're going to go right to the next node. Then, 8 is less than 10, so we will go to the left node. And 8 is greater than 7, so we would go right, but there's nothing here, so we found the position where we want to place 8. Now the binary tree is still in order, and we can find values without having to look at every element of the tree. So no matter what we're looking for, the amount of comparisons we do is less than the size of the tree. So to find 2, we do 3 comparisons. To find 8, we need to do 4 comparisons. So what would a binary tree look like in code? Well, we'd need a node object and a binary tree object. For now, we're just going to stick to storing one type of data, a character, but later on we can write code with templates that will be able to write one structure to store any type of data. A node will store some type of data and keep track of both of its neighbors. Generally, the left neighbor is less than, and the right neighbor is greater than. Our tree object will store a pointer to just the first node, or the root. The root is the first thing that is inserted into the tree. This right here isn't a full insert function. This is only the first step. First we have to check the pointer to the root node. If it's null, that should mean that the tree is empty. We will need to allocate some new memory for a new node, and point the root pointer to that new node. After we allocate memory for the node, we also need to set the data for that node to whatever was passed in the insert function's parameters. Note that in this example off screen, the node class's constructor will set the left and right pointers to null. And since we are allocating memory with the new keyword, we will want to make sure to use the delete keyword to delete this memory in the destructor. Now if the root isn't null, we need to expand this function definition to find a position for the new node and set it up. Implementing this would be easiest maybe with a recursive function. But for now we're going to cover this information with simple loops at first, then have a lecture on recursion, and then revisit searching and sorting. To begin traversing the tree, we start at the root. We will compare the new value to the current element's value, and figure out whether we need to go left or right. Here I've expanded just one of those directions. If we're going left, but no node is there, we've found the position for our new item. If we're going left and there is already a node there, we update our traversal pointer, the current pointer, and go back to the beginning of the loop. This functionality would be similar for also traversing right. This function could be much smaller and easier to follow if we made it recursive, but hopefully this version gives you an idea of how inserting data into a tree and keeping it ordered would work. Searching iteratively would work about the same, except that instead of searching for a null space, you're comparing the node's value to the search term parameter. Finding data in a data structure is more efficient if we have sorted our data ahead of time. If the data is unsorted, we could do a linear search or some form of divide and conquer, but we can't do a more intelligent search based on the ordering. Sorting is another area where there are multiple algorithms for sorting our data, and they each have their own trade-offs. The binary tree is a data structure that is built to stay sorted, which is enforced by how items are inserted into it. But we might also want to sort something more linear, like an array, after the fact, so that our search later on will be more efficient. Let's try one sorting algorithm for now. With insertion sort, it iterates over every element of an array except for item number 0. It picks up that element and it looks at each element behind it to see if there is a better place for it. Let's step through the algorithm. Here we start with an array of 6 characters. In the algorithm, we iterate through every element in order except for number 0. So we start with p equals 1. We store a backup of the value in the array at position p, which here is w. The j loop will begin at p and go until either j is equal to 0 or until the value at p is greater than or equal to the value at j minus 1. So here, w is greater than q, so we're going to skip the j loop. Next, p is 2, and its value is e. J starts at 2. It will swap the value of the array at position 2 with the value of the array at position 1. So now the array at position 2 will equal w. Afterwards, j is 1. It sets the array at position 1 to the value of the array at position 0. So now, array at position 1 is q. Then, once the j for loop is done, j is now equal to 0, and the value of the array at position 0 is set to e, which was stored earlier. And this algorithm continues until the array is sorted. So here's before and after. So that was a brief introduction to searching and sorting. We will cover more on this topic after we look at recursion. Though for many cases you'll end up utilizing someone else's sort functions, such as from the standard template library, since they are more optimized. After all, why reinvent the wheel?